Okay, good afternoon, everyone. My name is Courtney Mulholland, and I'm the current president of the GSC. I would like to start by thanking the U of A for providing today's Zoom meeting services. Today's presentation will be recorded and screenshots may be taken and posted on our webpage and social media platforms. Today's presentation, titled Hangingstone River Approach Fill Construction, a Case Study, will be presented by Tham and Tony Ruban. The presentation will focus on the geotechnical monitoring program used to monitor settlement and slope stability during construction of the headslope and abutment of the Hangingstone River Bridge on Highway 63, approximately 35 kilometers south of Fort McMurray. Tham is a senior geotechnical engineer and project manager with Tetra Tech Canada, Inc. Tim has practiced geotechnical engineering for over 25 years in Canada and overseas. He has extensive experience in various types of geotechnical design works. He has also specialized in slope stabilization designs, retaining wall designs, deep and shallow foundation designs, geotechnical monitoring, and finite element modeling. Tim has worked on the geotechnical aspect of and project managed projects from the public sector, contractors, oil and gas companies, consultants, and private developers. Tony Ruban is a principal consultant with Tetra Tech Canada, Inc. Tony has over 40 years of experience in geotechnical engineering on a variety of projects throughout Western Canada. Areas of expertise include foundations, slope stability, groundwater seepage, and water retaining structures. Tony has been involved with a wide variety of projects, including roadways, highway embankments, cut slopes, bridges, subdivision developments, excavations, cooling ponds, water reservoirs, pipeline river crossings, industrial developments, and commercial developments. Thank you, Tim and Tony, for agreeing to give this presentation. I will stop sharing my screen, and Tim, if you were able to share yours again, that would be great.
Okay, thank you. Just give me 1 second. So hi there, everyone. I'm glad to be here today, and thank you very much for joining us on this webinar. Today I'm going to present to you the geotechnical works Tetra Tech Canada recently undertook to facilitate construction of the Hangingstone River Bridge.
Tim, we can't see your screen.
There you go. How about now?
Yep. I think it's coming.
Oh, there you go.
Great. Thank you, Tim.
No problem. We'll start again. So that's great. Hi, everybody. My name is Tim, and Connie already introduced me. So thank you very much for joining us on this webinar today. We're going to present to you the geotechnical works Tetra Tech Canada recently did to facilitate construction of the Hangingstone River Bridge. In this webinar, we will talk about the geotechnical stabilization works we have implemented to maintain stability of the headslope. We will also talk about the geotechnical monitoring program that we have implemented and how it helped us to control field placement during construction, and how the monitoring results demonstrate that the stabilization measures worked effectively to prevent slope stability failure during headslope construction. So let's start with some background information on the project. Highway 63 Hangingstone River Bridge is part of the Highway 63 tuning project. Highway 63 is located over here along this yellow line. It's a major highway that connects Fort McMurray to, which is a major oil sands hub, in the northern Alberta to the central Alberta region. The circled area, this green circle area, indicate the location of the Highway 63 tuning project. It is located approximately 35 kilometers south of Fort McMurray. So in terms of the project team, these are all the major players of the project. Alberta Transportation is the client. Tetra Tech is the prime consultant covering project management, highway design, geotechnical engineering design. Dialogue is the bridge structural designer, and MPA is the hydraulic river channel design. Right now I'm going to go through the project timeline. The project started with multiple phases of geotechnical investigation from about 2008 to 2010. The detailed design work took place in 2011 to 2012. The project was on hold in 2013 due to budget reason. At that time, it was decided to construct the project in 2 phases. And then tender and construction of the first phase took place at around 2014 to 2015. The first phase consisted of some of the road and highway works and also the northbound link bridge. I'm going to go into the details on those later on. The second phase commenced in 2020, which is just last year, a couple years ago. Construction started in 2021. The second phase includes the remaining road and highway works and also the Hangingstone River southbound link bridge. Now let's zoom into this area and take a closer look. So this is Highway 63 before the twinning, and it used to be a 2-lane highway, meaning 1 lane each way. And because it is close to Fort McMurray, there was a lot of heavy volume traffic and heavy trucks going along the highway, and unfortunately sometimes people wanted to pass on the opposite lane, and this increased the risk of car accidents. So and after the first phase of the twinning project in 2015, which is shown on the photo on the right, the old Highway 63 here joined up with a new northbound lane to becomes the new northbound lane altogether, and then there was a new southbound lane constructed and joined up with the old Highway 63 to becomes the new southbound lane. So after the twinning, it becomes a 2 lanes or 4 lanes highway and 2 lanes each way. And I highlighted for you the location of the Hangingstone River, and where the Hangingstone River crosses Highway 63 is the location of the Hangingstone River Bridge. So, so let's have a closer look on the next slide. Now, after the twinning in 2015, as I have mentioned, there was a new northbound lane constructed and joined up with the old existing 63, Highway 63, to become the new northbound lane. The first phase, we have constructed the northbound lane bridge, and but the existing Highway 63 turns into the southbound lane, but the bridge over there has not been constructed yet. So it was still the existing twin culverts below the southbound lane. This is a more recent aerial photo. In 2021, you can see the southbound lane has been realigned closer to the northbound lane, and you can see the bridge has not been constructed yet. The river channel has been realigned, and at that stage we're still working on the approach fill for this southbound lane, Hangingstone southbound lane Hangingstone River southbound lane bridge. So now the works at this moment are scheduled to complete later on this year. So Hangingstone River Bridge, northbound lane versus southbound lane. So the northbound lane and the southbound lane has the same stability issues. We have used similar stabilization measures. We use the same monitoring system, and because of the monitoring system, we were able to collect data for the northbound lane bridge. And just before the start of the phase 2 for the southbound lane bridge, Alberta Transportation came to us and asked us to see if we can do some optimizations for the southbound lane. So because of the monitoring data, we are able to do some back analysis, and we were able to tweak the power walls, part of the stabilization measures, and reduce some of the piles in the for the southbound link bridge. So we optimized the stabilization measure design using the modeling results from the first bridge. And however, for this presentation, we will focus on the Hangingstone River southbound link bridge because of the time of the time limit of this presentation, and also the data presented to you is going to be more recent. So now this is a photo of the I'm standing on the southbound lane twin culvert, above the twin culvert on the roadway, and looking at the northbound link bridge. As I said, the two bridges are identical. So it is 52 meters in length, single span bridge. It has the approach fill height of 9 meters on one side and 10 meters on the other side. Here's the geotechnical information that we have obtained for the southbound link bridge. Northbound link bridge highly similar. We have the subsurface conditions generally comprises alluvial deposits underlain by weathered clay shells, which is interbedded by sandstones at different locations. Now, we have also noticed in the bore logs that under the clay shell descriptions, we've seen thinly laminated features, slick size, and subhorizontal beddings. So we have done some lab tests on the clay shells, and we find out the peak angle of shearing resistance is about 15 to 25 degrees, and the residual angle of shearing resistance was only 7 to 8 degrees. So very low shearing resistance. And how? So we'll now talk about how does it affect the approach field construction. So when you have the scenario like this, where you start placing fill for your proposed bridge, it is going to cause this imbalance loading is going to cause potentially is going to cause forces onto the weak clay shell, and it is going to cause stability issues for the headslope. So and the problem is we do not know where that shear plane is going to be. Okay, so to deal with that, we have proposed a few stabilization measures. First of all, we replace the alluvial deposits with a gravel key, and then we also put in a power wall, 1.5 meter diameter at 3.75 775 meters on center spacing, and we also have geogrid layers. The purpose of that is we try to extend the slip surface as far as possible away from the headslope. However, with all these stabilization measures, we still have a second problem, and let me show you why. This is the assuming conventional construction sequence. So we have the gravel key and the power wall in place. We usually put fill up to the base of the abutment, base level of the abutment, or top of the abutment pile, and we'll start doing piling for the abutments, and then we will carry on with the abutment constructions and also the rest of the approach fill placement. The problem with that is by the time you finish up the abutment, a slip surface might have been created, and the slope would start moving, and by the time you finish all the fill placement and the slopes become stabilized and the settlement becomes stabilized, your abutment and your pile will be out of place from the original design position. That's no good. So what we end up doing is we modified the construction sequence. In our case, we first of all we install a bunch of monitoring devices, and so we have instruments in the power walls, in the ground, and also we'll talk about in details what they are. And then we will fill all the way to the top for the approach fill, the full height of the approach fill. And then we'll also monitor the settlements at the top of the fill. Once the movements becomes stabilized and subsided, we then excavate down and to the pile level locations, and then we begin piling. After we finish the piling, we complete the rest of the abutment. So if we do that, it helps to reduce the movement after abutment pile construction. So the geotechnical monitoring system and their key objectives are to confirm that stabilization measures are working effectively, and it helps to monitor movements closely to control the rate of field placement, to reduce the likelihood of slope failures, first of all, and it identifies when movements have become stabilized to reduce the likelihood of movement after the abutment piles are installed. So what kind of geotechnical monitoring instruments we have installed? First of all, for lateral movement of the ground, we install slope inclinometers, or SI. We have two types. The first type is in-ground SI, which is installed into the ground. The second type is installed inside the power wall. It is called we call it in-pile inclinometers. And we also install wiping wire pulsometers to monitor the pore water pressure changes during field placement. We also have settlement cells. If you look closely, the green ones over here, and survey hubs at the top of the field to monitor settlements. And we also, because these are electronic devices, we also hook it up to a data logger to collect data. Now, this is what it looks like on plan view. The wiping wire pulsometers is right there. Inclinometers are shown by the triangle, and the settlement monitoring points, the survey hubs at the top, are shown over here. Settlement cells are located in the same borehole as with the wiping wire pulsometers, and also we have a data logger, and that's the cable trench. So now let's go through some of the installation photos so you have a better idea what they are. So what you're seeing right now is on the left hand side is the hanger hanging onto the cage, and the SI being lowered into the cage. The reason we do that rather than fixing it to the cage is because when the cage is lifted, the SI may be damaged by the bending of the cage. Now, once you lower it into the cage, and we lift the cage, and then so that we can tie the two together with wires. And that's what it looks like when it is all done. And then we can start concreting. And during concreting, you may want to fill up the pipe with water to counteract buoyancy of the pipe. And this is what it looks like when it is finished. And so that was the in-pile inclinometers, and in-ground inclinometers is the same thing. Hopefully some of you are already familiar with the installation. It is done same way, but except it is done in the borehole. And this is a photo of what it looks like. So the in-pile inclinometers and the in-ground inclinometers before any fieldwork was being done. Now, also notice that the pipe has been extended a little bit to allow fieldwork. This is a very important step. When extending, you usually extend the SI before the filling work. So when the filling work comes in, it is very easy to damage the SI. So the contractor needs to work carefully around the SI pipe. You can put casing around the SI pipe if you want to protect it better. But in this case, we did not. We just go with just the SI and working carefully around the pipes. So the next instrument I'm going to talk about is the wiping wires and the piezometers. So what we use for sediment cells, wiping wire sediment cells and wiping wire piezometers. So wiping wire sediment cells, we use the Geocon 4600 wiping wire sediment cells, and it is installed inside a borehole. And there are a few major components, including the wiping wire pressure sensor to be installed at the bottom of the borehole, and a reservoir at the top of the borehole, and a liquid line that connects the wiping wire pressure sensor to the reservoir, and a cable that leading from the sensor to the data logger. We find this borehole type sediment cells quite effective based on our experience. In terms of wiping wire piezometers, we use RST VW2100, and we tie them along a pipe together with the wiping wire sediment cells. They are all installed in one borehole, and we connect both of them to a data logger. And let's go through some installation pictures. So we drill the borehole with a drill rig. We tape the wiping wire sediment cells at the base of the pipe, a PVC pipe, and then we also tape the piezometers along the pipe. Then we start pulling, we insert that into the hole, and then we start grouting and then pulling up the casing. By the time the casing is out completely, you can see the reservoir from the wiping wire sediment cells and the other cables coming out of the hole. This here is the sediment plate. It is right now is upside down. It is going to be connected to the reservoir and then placed at the top of the borehole. Of course, we top up the grout and then also fill it up, backfill the area with sand. So the cables will run along a cable trench, and it is going to be inside a conduit, and then the cable and the conduit is going to be covered by sand, backfilled with sand, and the cables then get connected to a data logger, and then that's how we hook it up. Now the next item is the survey hubs. These are simply pins installed in a grid pattern after the fill is completed. In this particular case, we use 10 meter spacing. There are 5 rows on each abutment, and typically the survey hubs are 5 meters apart in this direction. So this is what it looks like in a view. So just a pin into the ground, pound it into the ground, and if there, in some cases, there's a concern in terms of frost checking, we would put a sleeve around the pin. Now, geotechnical monitoring system, apart from the instruments, we also need to take a look at the monitoring frequency. So we collect monitoring data on a weekly basis, but it is subject to change if necessary. Field placement rate was set as 1 meter per week. In this case, we did not change it. Movement criteria was less than 2 millimeters per week for 3 consecutive weeks. I'm going to explain that later on. Now, here in this part, we're going to talk about the monitoring results, which is also the last part of this presentation. So we will now first of all talk about the settlement cells and the vibrating wires, and how do we present the results. These numbers corresponds to the serial numbers of the settlement cells and the absorptors. So first of all, this is an Excel spreadsheet. We have elevation shown on the left hand side, and then settlements on the right hand side. So a secondary axis, y-axis, and time is on the x-axis. Notice that this is the final grade, and this is the original ground level. During construction or field placement, we recorded the field level, and we plotted against the elevation, against time, along this y-axis. So this is the level of the field placement. As you can see, it reaches the final grade, and as I mentioned before, we modify the construction sequence so it comes back down. And this is where we are right now, the field level, because of the winter shutdown. And this is the settlement recorded by the settlement cells. As you can see, the settlement increases gradually with the field placement, and then pick up all of a sudden, and then eventually it slows down with the after we stop doing the field placement, and then it gradually reduces or plateaued along approximately 140 millimeters. For vibrating wire piezometers, what you're seeing is the location of the piezometric of the tube of the tip of the vibrating wire piezometers, where we have installed them, and this is the recorded pore water pressure. We see a slight increase of pore water pressure, and then it's slowly dissipated after we finish the field placement. So when you put them all together, this is how we present our graph. So field placement elevations, settlements from the settlement cells, and the pore water pressure from the vibrating wire piezometers. This is for the self-abutment. And I just put in a line to indicate where we have stopped filling, and then the sediments start to slow down and plateau. Now similarly, we have done the same thing for north abutment. This is the field placement. Pore water pressure changes during field placement, and the settlement recorded by the settlement cells. Okay. For the north side, it is slightly higher field height, and we were recording around 150 millimeters. And this is where we stop the field placement. So next one, we're going to talk about the inclinometers readings, which is very interesting as well. We have two in-pile inclinometers and two in-ground inclinometers. So let's start looking from the south side. So SIO1 is the in-pile, SIO2 is the in-ground. We'll look at the in-ground first. So the in-ground inclinometers, and for those you do not know about inclinometers, is the A direction is approximately the direction, movement direction pointing towards the river. On the left hand side is the cumulative deflections, and the incremental deflections is shown on the right hand side. At center is showing you the dates of the readings. So the incremental is showing you the difference between the two readings. And over here we can see a very distinct shear plane occur at around 483 elevation, and you can see almost the same thing on the cumulative plot as well. There has been a movement around 483, and with originally, if you look at it with time, is that this is slowly reducing in terms of slowly plateauing in terms of movement. So that's A direction. B direction, sometimes the inclinometers is not pointing very well towards the river. The B direction is parallel to the river, so we also register some movement in the B direction as well. Similarly, you can see a shear plane developing on the inclinometer plot. If we plot the resultant of A and B against time, you can see it start picking up in here, and then it carries on with the field placement, and then after field placement is completed, it starts slowing down and then plateauing around 70 millimeters or 80 millimeters. Now, in comparison, this is SIO1, which is the in-pile inclinometer. You don't see the distinct movement anymore because the pile wall is smoothing it out, because you cannot have a brick, or it is more difficult to have a brick along the pile wall. And so after it has smoothed out, it still moved quite a bit to around 60 millimeters, and that is the B direction, and that is what it looks like when you plot it against time for the resultant. Similarly, for the north side, we have SIO1 north is the in-pile, SIO2 north is the in-ground inclinometers. And again, we have a shear plane developing. This is north side of the river at around 483. Again, this is indicating a spherical plane occurring on the cumulative plot. This is B direction, so almost this one installed pretty well. It's not pretty good. It's not registering any movement in the B direction. And so I just plot A against time, and this is what it looks like when you plot the movement against time. So approximately 100 millimeters in that case. And for the one in pile, again, it's the pile smooth out the shear plane, and it basically move in this fashion, and it registered almost 120 and 130 in terms of lateral movement. Again, as field placement continue, we have the movement picks up, and then it starts slowing down after field placement. So are these lateral deflections similar to what we expect? Now, this is the finite element model that we have prepared in the design report, and we predicted about 120. Now don't forget, these were done by back analysis, and we have a lot of great information coming out from the North Mountain. And with that information, we are able to optimize the power wall and the stabilization measures. So for the survey hubs, this is what it looks like when you look at it on plan. We mentioned that already, that this is about 10 meters apart. So 10, 20, 30, 40. There are 5 rows of survey hubs. So we do an average of the 3 readings and present on a plot like this, against settlement, against time. And we'll scroll through from row 1. This is the result from row 1. This is the result from row 2. Row 3, highly similar. And then row 4 is getting less. And row 5 is getting less again. Now, part of the reason for that is because the fill height, as you move away from the head slope, the fill height actually get less because the existing ground is actually covering up. This is the result for the north side. Again, for row 1, average of row 1, we have about 35 to 30 millimeters, 35 millimeters before the start plateauing. And for row 2, row 3, row 4, and row 5. Now, in this case, it's distinctly, the settlement is distinctly less than the previous rows because of the fill height. Now, just for comparison, we have plotted the survey hub results of North Abutment just for row 1 and compared with the settlement cells. So this is the survey hubs results. This is the time that we finished the field placement, and we when we put this, and we put the survey hubs on top of the field. And this is from the settlement cells, recording right here. You can see a slight difference between settlements there, and eventually it is getting less and less and have the same trend. So in summary, in this presentation we showed you how we implemented the stabilization measures and geotechnical monitoring for the Hangingstone River Bridge for the southbound link. Northbound link is highly similar. As you can see from the monitoring results, the shear plane did develop during the headslope construction. So the geotechnical issue, the threat, is real. It is a real problem. Pore water pressure development was limited. There's only a little bit of pore pressure increases, and then it dissipated very reasonably quick. And the rate of field placement was controlled, and the time so that it is not too fast, such that the movement becomes too severe, or it causing slope failures. And we also use the monitoring system to control the timing and to find out the timing of the ground, when the timing of the ground movement to become stabilized, so that we can come back down and do the abutment foundations without it being adversely impacted. And the monitoring system shows us the stabilization measures work effectively and prevented slope failure during field placement. So overall, the instrument results were very good, but it could be largely due to the fact that we were directly involved in installation and monitoring. So rather than leaving it to the contractor, in other instances when the installation were done by the contractor, the results were not the same. as good as what we see in here. So I guess a key takeaway of this presentation is to have good control on installation and monitoring. Now that should conclude my presentation. So if there's any questions, please let us know.
Perfect. Thank you, Tim. If anyone would like to ask some questions, you can type it into the chat box. It's usually the best way. So we have a question from Sean. Based on the information obtained, what would you change in the stabilization design or construction?
Based on the information that we obtained, how would we change the rate of construction? Was that the question?
No, based on the information obtained, what would you change in the stabilization design or construction?
We have not, well, I think right now it is working effectively. So if you mean that if we are going to do it again, I think the monitoring results is showing us that the current stabilization measures and method has been working effectively. So I'm not sure if that answers your question. So
I don't think we would have done anything differently. The way things turned out, the results were actually really good in terms of giving us a comfort level that we were able to intercept that failure plane and the pile wall, as Tim mentioned, based on the original information from the north head slope, we were able to optimize that pile wall design, and we were able to shorten the piles, and as a result presented some savings associated with that. So and the thing that I thought was particularly unique was just how much settlement we got out of, we ended up replacing the soft alluvial deposits and replaced that with a gravel key, and then the fill was placed on top of that. 150 millimeters, considering that the underlying material was bedrock. Now the upper bedrock in particular was fairly weathered, but we still saw what I consider a fairly significant amount of settlement with the it wasn't a huge amount of fill that was placed, but when you consider you got 150 millimeters of settlement out of that, I found that part kind of surprising. But having the settlement cell included as part of the instrument package gave us that information and understanding of just how much settlement we actually were able to observe. So, not sure we'd have done anything differently. It actually worked out really good, which is why we're making this presentation.
Perfect. Thank you. Mike asked, did you have problems with air getting into the lines of your settlement cells? Did you have the capability of de-airing the lines with this type of installation?
In this case, we do not have air problem. I am not sure if this is because the type of cells that we are using allow us to have everything prepared and then just go to the site and install into the ground. Now, I understand, I know exactly what you're saying regarding the air, but we did not have this problem this time, and we did not have problem last time when we were doing the knock mounting. I have to check. I don't know if there is a de-air device. If we have a de-air air problem. Now, don't forget, this is being buried into the ground. So if there is a de-air problem or an air inside the tube problem like the other type, we may not be able to access the reservoir. So because it is deep into the ground already by the time, but actually some of these instruments, like for example the northbound link, has been used for quite some time. They are still being monitored after 2015, 2016 by Alberta Transportation, and so we do not. I have not hear that they have air get into the system problem yet. So, which is I think is pretty good.
Perfect. Thank you. And then we have Ian asked, did you model the abutment without the pile wall? I presume you needed a much flatter head slope.
That is exactly the problem, because a flatter head slope would actually require a longer bridge. So a longer bridge may be more expensive than this. And don't forget, we're talking about shearing resistance of 15 degrees if at peak, 7 degrees at residual. So I don't know how flat you need to be in order to not using a stabilization system.
Thank you. And Colin asks, great presentation, Tim. Can you elaborate as to why the shear key was required in addition to the pile wall? Was this a constructability item?
Okay, so imagine that we are just putting the pile wall in. What do you have around that pile wall? You have the alluvial deposit, which is maybe even weaker than the clay shell below. So in order to help,
Tim, you got to speak louder.
okay, so in order to help, how about that?
Better.
Okay, in order to help you, in order to help the whole system to be more stabilized, having this gravel key actually helps quite a bit. It is right at the top of the pile where it wants to move the most, as you can see on the monitoring plot. And when it moves, it helps to give some resistance because of this gravel key. That's what I find out during the analysis.
Great. So we have just a few minutes left, and we have two more questions. Oops. Was there a maximum deflection criteria that the pile wall was designed to accommodate?
Yes, we after we done our analysis, we pass on the information to our structural designer, and the structural designer work out corresponding structural design for the pile. And yes, there's a maximum deflections for the pile wall. I cannot remember what that is, but
It was a bit of an iterative approach. It was kind of a back and forth in terms of they would give us an initial section, we'd analyze it, and then they'd take a look at whether or not they could optimize it, and if so, we would have analyzed a number of different sort of pile configurations to sort of get the amount that the structural engineer felt was tolerable.
Someone asked a follow-up question about the pile design. They asked if it was governed by shear capacity or deflection.
It was bending, I'm pretty sure.
It is deflection induced bending. So it is, Tony is right, bending.
Okay, and then we have two questions about the shear resistance. Was the shear resistance of the soil back calculated or measured? And did the design assume all residual strength, or was it a combination of peak and residual?
I would say a combination of peak and residual. So in the that's one of the tricks you have to do, is to induce the movement, and so you can assume a failure plane and then assign residual along the failure plane. The rest of the slope you can assign non-residual values.
Great. I think that was the end of all our questions. Thank you so much, Tim and Tony. That was fantastic. Really appreciate your presentation today.
You're welcome.
For the rest of you, just a few reminders. Our 2022 annual general meeting is next Thursday, May 5th at 12 p.m. We'll have a presentation from Jean Hutchinson. The event notification will be sent out soon. Also, the deadline for nominations to the 2022-2023 GSC Executive Committee is tomorrow. Nominations can be sent to gsc@geotechnical.ca. All nominations must be current members of the GSC. Finally, the U of A Geotechnical Center is hosting an international short course on design and assessment of mine waste structures between May 12th and 17th, 2022. Perfect. Thank you, guys. Thank you, Vivian, for hosting.